Okay, so now we're on the last video for aromatic compounds. So for aromatic compounds, the most signature thing that we know about it is that our favorite benzene ring. So let us first understand the theory behind why benzene ring exists. So this based on the idea of resonance stability. So resonance stability mostly occurs when we have like a double bonds, you know. So there are actually two forms that this so we call it so this is our cyclohexene. So it's actually one two one three oh wait, hold on. So 1 3 5 cyclohexene, and we have our wait about 2 4 6 cyclohexene. Yep. So the thing is that these double bond can break and then they can just form here, and you can form this structure, and it's similarly you can break and then form this structure here. So it exists as like two structures, so therefore it's a resonance stable structure, which is this. And we draw a circle to represent, or like the to have like the partial double bond over the entire system. So that's how resonance stable structure works. Okay, so if you look over here, we have our benzene ring. Then we have an interconnector ring of 6 carbons with their that is sp2 hybridized. So recall sp2 hybridized. I have 3 sp2 hybrid orbitals and 1p orbital. Because how do you tell? Because trigonoplanar carbon bonded to 1 2 3, which is the hydrogen atom here. So I'm bonded to 3 different groups, and I have a p orbital to store my lone electron. So since they are adjacent to each other, they kind of overlap to form an interconnected ring of pi electrons. So if we can illustrate over here. So like I said, this has p2 hybrid orbital. It's a carbon. So this is your p orbital. This thing right here. And the rest are all your sp2 hybrid orbitals. So over here you can look at the energy level diagram. You can see this. If we were just to leave it in a double bond form, it's really not so stable as compared to this resonance stable form. As you see it on a lower energy level. This is just cyclohexane for comparison. So therefore, the idea of resonance stability comes like that. Okay, so when it comes to elucidation question, it's very a useful tip is that, for example, they show a compound like C8H9. So when you know, how do you know like a benzene ring exists? So firstly, the number of carbon must be greater or than or equal to 6, right? Then the C to H ratio must be 1 to 1 or approximately 1 to 1, because 8 and 9 is actually close. But if we were to talk about H12, then of course that's not highly likely lah. Alright. So if we were to understand this whole resonance stability thing, then now let's take a look at these two weird compounds here. So now I have, instead of like all 6 carbon atoms, so maybe one of them is like is a nitrogen atom. So over here I have 2 different structures. It's very unique. So when I look at A here, I see this nitrogen atom. It's of course it's sp2 hybridized. Okay, so it's the same hybridization as our carbon in the benzene ring, but the weird thing is that it has its lone pair of electrons here, so it's not bonded to H like over here. So let's not confuse both. Right, so what actually happens here is that in the sp2 hybridization of this nitrogen atom, I have a p orbital and 3 sp2 hybrid orbitals. So because the sp2 hybrid orbitals are used to form bonds, right? So and I have one sp2 hybrid orbital used to store my lone pair electrons. Therefore, this compound is actually basic because it can donate 8 lone pair electrons. Whereas if you look at here, my sp2 hybrid orbitals, 3 of them, 1, 2, 3, are involved in bonding, so then my lone pair electrons are contained in my p orbitals. And over here, this p orbital will then overlap with the other p orbitals, adjacent carbon, and then really localized over the benzene ring. Therefore, it's not available to donate to, therefore it doesn't display basic properties. So, why does benzene ring prefers to undergo electrophilic substitution instead of electrophilic addition? So because of the p orbitals overlap of adjacent carbon atoms in the benzene ring, it forms an interconnected ring of pi electrons, which gives its resonance stable structure. So if it undergoes electrophilic addition, it means it will have to break the interconnected ring of pi electrons and it will lose its resonance stability. So therefore it prefers to retain its resonance stability and hence its aromaticity. Therefore, it prefers to undergo electrophilic substitution reaction. So when does benzene ring becomes a substituent? Because we know phenyl 2,4-DNPH, phenyl hydrazine. So when does it become a phenyl and when does it become a benzene ring, like the main thing itself? So for example, if we were to look at this structure here, so it's like an RX. Why is this an RX instead of a halogenal benzene? So because we look at this bromine atom here, it's connected to the carbon that's first connected to another carbon that's connected to the benzene ring. So it's not a direct connection, so therefore this benzene ring becomes a substituent. It's for phenyl. Alright, so what are the reactions that we learned in our syllabus? So there are actually 3 reactions. The fourth one being a Friedel-Crafts acylation, which is not really in syllabus, but it works kind of the same as how the rest goes. So for Friedel-Crafts acylation, I'll be attaching an alkyl group to the benzene ring. So it can be a methyl group, it can be a ethyl group, etc. Then for halogenation, I'll be substituting one of the hydrogen atoms for a halogen atom. Nitration is the same, but except I put a nitro group, NO2 group inside there. Alright. So, not in syllabus, it's Friedel-Crafts acylation, so it works the same as your Friedel-Crafts alkylation, except the electrophile is this thing here. Right, we still have our anhydrous catalyst. So what are the reagents and conditions? So for our Friedel-Crafts alkylation, we definitely need anhydrous AlX3, or we can use anhydrous FeX3. Now for some MCQ question, they're going to say just use Fe. So it's a possible catalyst as well, but you do not need to know like how it forms interaction with the halogen atoms. Alright, so this anhydrous is very important because if you recall under periodic table, if we use the aqueous condition, this will hydrolyze readily in water, and then it cannot perform its function anymore. Alright, then of course we need our CH3X. Right, for our Friedel-Crafts alkylation. For our halogenation, it's the same set of reagent condition, except instead of my RX here, I will use X2 in CCl4. And I will specify TCl4. But if we are going to do, for example, halogenation for a metabenzene, then of course we have all these set of reagent conditions here, just that we need to say in the dark, because we would want FRS to go on here. Yeah, we only want the halogen atom to attach to the benzene ring. Then for nitration, it is corn sulfuric acid, corn nitric acid, and 55 degrees Celsius. So must remember the temperature. For Friedel-Crafts alkylation, it's more or less the same set of reagents as a Friedel-Crafts alkylation, except we use an acyl halide here. So now looking over at our substituents, so we have two types of substituents that can attach to our benzene ring, and it's also these types of substituent that will test us in our concept of acidity and basicity. Okay, so we have two types of substituents. One of it is an electron donating group, and the other one is an electron withdrawing group. So electron donating group, in other words, they are activating group. So what they do is that they make the benzene ring more electron rich. So for CH3, it's more of like an induction effect. So it kind of make it more like we say, like electron donating alkyl group, but they don't really. But the extent of like increase in the electron richness is lower as compared to our OH and AH2, because the lone pair of electrons on O and N delocalizes into the benzene ring, therefore making it more electron rich, therefore it's stronger activating group. If we were to compare here at electron withdrawing group, typically it's compounds that have double bonds, like for example NO2 here and our COOH here. Then it's also our halogen atoms. So mind you, please take note, because a lot of people might confuse this. So they might think that, oh, all EWG are 3 directors, or EDG are all 2,4 directors. So that's the misconception. Please note that yes, all EDG are 2,4 directing, but our halogen, this attached to the benzene ring, is 2,4 directing, whereas the double bond electron withdrawing group are 3 directors. So then you ask, oh, what's 1, 2, 3, or 4 directing? So for example, let's start with the topmost carbon: first, second, third, fourth, fifth, sixth. So for example, I have a methyl group over here. So methyl group is a 2,4 director. So that means my substituent can attach here or here. But it also has a possibility of attaching here, because if I were to name it from the other way around, I'm going to write in black pen. So 1, 2, 3, 4, 5, 6. Notice how the position 4 stays the same, but my 2 and 6, they are interchangeable. So there's a possibility of the substituent occurring there. So electron withdrawing group are the activating group. So it makes it less electron rich. So this electron richness has something to do with the conditions that we use for reactions. So activating group make it more electron rich, therefore we use milder condition. While for deactivating group is less electron rich, so we need stronger conditions to react. Okay, so there are so now we're gonna ask why no nucleophilic substitution for our benzene. Why does it go ES reaction, right? So there are actually 3 arguments to this. So first thing, we'll talk about the strength. So there is a partial double bond character, because if you see here, our hydrogen atom, it has its p orbital, even though it doesn't form a pi bond with the p orbital of the carbon atom in the benzene ring, but it overlaps slightly, right? So it gives a partial double bond character. That's what we mean. Therefore, it's very, very hard to break, and it doesn't really undergo NS reaction, unlike your RX. Right. The second argument is because of steric hindrance. So we have our bulky benzene ring over here. It's quite a big group actually. So therefore, whenever you see, like for example, like a phenol, it is actually, I'm not sure if it's soluble in water or not, but my guess would be it is not really that soluble. So yeah, because it's a very, very big benzene ring. Actually, I think we can think of a better example, much more clearer one. So then I have lots carbon, then yeah, like a OH group here. So even though you can form hydrogen bond, but the energy release from this hydrogen bond formed between this this and water molecule is insufficient to overcome hydrogen bond between water molecules and the predominant ID-ID interactions between this molecule here. Yep. So that's the solubility, and when we talk about electron-rich benzene ring, the electron richness. So benzene ring is very electron-rich. So our nucleophile, remember, they are a bond pair electrons. So what it does is that our electron-rich benzene ring actually repels the nucleophiles. So that's why it doesn't undergo nucleophilic substitution. Okay, so how about our substitution now? So we will see quite a bit in our when we ever do a organic chem question. So it'll be like, oh, synthesize, propose synthesis pathway as to how to synthesize the certain compound. So for example, if you want to synthesize B from A, we can just simply do halogenation because methyl group is a 2,4 director, our NO2 is a 3 director. So for example, 1, 2, 3, so then up here, over here is 1, 2, 3, 4 with respect to the substituents. So it just so happened it coincides, so yeah, it works. But then if you were to look over here, if you were to obtain B from A, then I'll be looking at I'll be substituting with respect to my NO2 group. This is 1, 2, 3. So therefore, third position because it's a 3 director. But if I were to obtain C from A, I'll be looking at my methyl group. Right, so it's a 2,4 director. So 1, 2, 3. So it's possible here. Yep, so there we go. Yep, so this is the thing that you have to look out for. So you have to be aware which functional group are you looking at and substituting with respect to which one. Okay, so now we're going to look at our final mechanism here. It's called electrophilic substitution. I must write out the full name. So we'll be using Friedel alkylation as an example. So remember it said here this why we use the Rx, right? The reason why we use an Rx is because as with our halogenation reaction, we use an carrier, which is an anhydrous. So our halogen atom will actually go to our carrier, so which is what you see here. So it must correspond. So we use Br atom, so you must use AlBr3. If you use Cl, then you must use AlCl3. Then you have to generate our electrophile, which is an alkyl group electrophile. Then our electron in our benzene ring will attack our electrophile and it will form this structure here. So please note it's a slow step, and do note that our benzene ring now actually open, so we must draw this U shape. So the tip touches the adjacent carbon to the one that has become sp3 hybridized. Right, so now it's formed 4 bonds. So then after that, bond pair electron here that's attached to the hydrogen atoms, the CH bond, will actually break heterolytically because now I want to restore my resonance stability, resonance stable structure. So my electrons will enter the benzene ring and my H will break off, but my CH remains here. So plus my carrier, then I'll get my methyl benzene, and I have my HBr because the H here and the Br that originally was donated to here is now here, and we have regeneration of our catalyst. So these are the 3 steps. So now we consider the acidity and basicity. So for example, we have our benzoic acid that we're looking here, and with our phenylamine. So when we look at our acidity and basicity, we are aware that there are substituent groups, right? So this is an activating group, this is a deactivating group. So when with respect to acidity, we're looking at the stability of the benzoate anion. So we're doing either how dispersed this negative charge on O is. So knowing that this is a benzene ring, so of course the negative charge will be delocalized into the benzene ring. Now we use the phrase negative charge delocalizes into benzene ring and not the lone pair of electrons, right? So this is a common phrasing error, so just avoid that. So now with respect to the groups here, so what we want to do is that we want to stabilize this even more. So that means I disperse even more, delocalize even more into the benzene ring. So how I do that is that it's more preferable to have a EWG so that the negative charge is more delocalized into the benzene ring. So therefore this is more acidic as compared to my phenol because it's the activating group. So the negative charge will be delocalized over the benzene ring to a lesser extent. But compare that with phenylamine, it's slightly different here because over here is I'm looking at how readily available my lone pair electrons on n atoms are for donation. So it will be more preferable to have an activating group like OH as compared to a electron withdrawing group. So this is more basic. So one common thing that people possibly make errors that they think this is the same as this. These are very different. So this is called phenol and this is methanol. So this methanol is an alcohol. This is a phenol. It's OH directly attached to a carbon in the benzene ring. It's very different. But it won't be different if you say that, oh, H2OH. Yep, if it's something like that, then yeah, this is actually an alcohol, right? Because it's not directly attached to the carbon in the benzene ring. Okay, so now the thing is that phenol is actually acidic. Why? Because this negative charge is actually delocalizes over the benzene ring. So therefore, it's more stabilized and therefore this dissociation is more preferred as compared to the dissociation of your H plus from your alcohol as we discussed earlier on because of the electron donating alcohol group which intensifies the negative charge. Okay, so now we're going to consider the reagents and conditions for our groups here. So we have our activating group, our OH, and your amine, and also your methyl group. So when we look at nitration, we can look at these set of reagents and conditions here because CH3 is a weaker it's a weaker activating group. Therefore, we expect to have corn nitric acid, corn sulfuric acid, but a lower temperature at 30 degrees Celsius. Whereas for our stronger EDG, OH, and NH2, we can use nitric acid, aqueous, or if you want, this is all mono sub here. This mono sub. But if you want tri-substitution to form a yellow PPT, then we must make sure that we have our corn nitric acid. And there you go, that's your yellow PPT. So for halogenation, it's also about the same, just that for methyl benzene, we have our same type reagents, but in the dark because there is this alcohol group here. We don't want FRS to undergo there. So for halogenation for our OH and our NH2, this activating group, you can just use X2 and CCl4 monosub, or you can use aqueous for trisub. So it's a white PPT form. So these are all possible compounds except for this. So make sure that you have at least one atom over here, one X atom. Can't be just all 3 R groups. It's not possible on the 2, 4, 6 position. So try substitution, we're looking at 2, 4, 6 positions. So 1, 2, 3, 4, 5, 6. So 2, 4, 6. Alright. So first on this is how we convert a metabenzene to a benzoic acid. So this is a strong oxidation, and thus we can only use KMnO4 aqueous, sulfuric acid, and heat. Now the condition to convert a metabenzene to a benzoic acid is actually very um, unique here. So the criteria is that we must have a benzylic hydrogen. So what is a benzylic hydrogen? Benzylic hydrogen means a hydrogen atom attached to the carbon that's directly attached to the benzene ring. I don't care what R groups here. It can be alkyl groups, can be hydrogen atoms, but minimally one hydrogen atom. And therefore we need to use a strong oxidizing agent. So if a question would ask you, describe what happens when I use potassium dichromate instead, and I thus with you have a benzylic hydrogen, please note that CH3 is not oxidized unless prolonged heating. But if there's any other groups on this benzene ring, for example, H2OH, then yeah, this will be oxidized to a carboxylic acid. But this whole thing will not be oxidized to a carboxylic acid, okay? So the products are from CO2 and H2O. The number of CO2 depends on how many excess carbon that you have on the alkyl chains. So if you have only one carbon, it shouldn't form CO2. But if you have like C2H5, then yeah, they'll form a CO2 molecule. But water molecule will always be there. So these are the special reactions that we have. So even though two R groups, carbon directly bonded to OH instead of like a H atom, but still considered to be strongly oxidized. So it's the same set of reagent condition. Same for this. Right. So you can see the 1O is CH3 here. So this is actually what we call it as phenylethanone. Yeah, phenylethanone. So it's still oxidized to benzoic acid. Now then we look to the other reactions. So here we have phenol again. So you do a redox reaction, same as alcohol, and you give your half H2 gas. Now we don't use it as distinguishing test because it's very reactive. But we can also react with NaOH to form the same thing. Now what we do here is that we form a we often conduct this to produce a better nucleophile. We call this the deprotonation reaction. Because over here, that's we only have one lone pair of electrons on O atom, but because we have here, we have two lone pairs of electrons on the O. Let's now have a So in a sense, there is an additional lone pair of electrons on this O atom. It's now O. There's a negative charge on it. So therefore, it makes it a better nucleophile and more reactive. So when it reacts with acyl chloride, it's of course the nucleophilic substitution because it's O atom. Bond pair electrons on O attacks this electron deficient carbon, removal of HCl, it forms the ester bond. Okay, so same thing as well. If I react with your carboxylic acid, phenol and carboxylic acid, it will form this ester bond as well. And if I look at phenylamine, it's about the same thing as well. If I react with acyl chloride, I'll form an amide over here, phenylamide. So the rest of the possible substituents are called benzaldehyde, benzoyl chloride, and phenylethanone, as I mentioned earlier. Okay, so these are the very fundamentals that you need to know for organic chemistry. So once you master content, the rest will be identifying reactions and how synthesis pathway and stuff like that. So this is the whole entire mind map on organic chemistry, and I hope you enjoyed the whole series. And yeah, Again, like I say, I'm not a master at this. I'm no master at this. As I'm doing this, I'm still learning along the way and memorizing things along the way. So I did not do this out of my own memory. I At least 30% was attributed towards looking through my notes again. Case, but I hope that a lot of the concepts are explained quite clearly, and that it really helps you in your revision. And yeah, getting content is about 50%, or might say like 40%, and mastering your skills by doing extra paper is really the key, because what A-level paper said is really not just content, just like it's more of synthesis, how you see the pattern and mechanisms you've never seen before. So it's a lot more of like electron moving and stuff like that. So yep, thank you for watching, and we hope you have a great day ahead.